Hello, fellow procrastinators. Today's guest is Renaud Lambiotte. Renaud is an associate professor at the Mathematical Institute of Oxford University, and he investigates processes that take place on large networks. In the episode, we talk about historian science. We talk about the joy and value of exploring without a particular purpose. We talk about doing a PhD without publishing any papers. And we talk about how reading classical texts by Boltzman and others, how that has shaped the work that Renaud does even to this day. It's an exciting one. Check it out. Now on to the episode.
Yeah, actually, so I always come to the room of my little one for anytime I need to do a Zoom meeting, because I can stand, which is because I don't like to stay to sit all day.
No.
And also he just has like this piece of furniture that has just the right height, so that I can put my computer and my iPad, and I'm somehow settled, and I'm surrounded by the magic of childhood. So wait, just take my coffee because it's supposed to be
Yeah, very good. But we should get started. We should get to stuff.
Yeah, exactly. So I just had, so let me see. So I just had like a few like images that I can use just to contextualize at some point, if it's okay. And I might write one equation or two,
of course,
just so that it's written. But it's I hope it follows the rules.
Absolutely, there are no rules, man.
Yeah,
we're just having a conversation about a paper that I was too lazy to read.
The way I see it, it's a bit like a conversation we might have, because even in a pub, right? At some point, you grab one of these things that you put under the beer, and you can write something. Mm-hmm. So actually, it's just a pity that I don't have like this kind of layout for my screen to have the shape of a Carlsberg stuff. I don't know what is the name of this small piece of paper that you put under the beer. Do you know?
I think if you put it under a pot, it's a trivet, but you know, I don't know. I know, like my mother-in-law is American, and she has some, and she likes our kids to use them on certain tables. So I have heard them, but by right now my brain is not giving me any information.
That's fine.
What they're called. But we'll get into it, and then you just screen share the stuff, and then we'll talk about it. And
just check if I have the link here. Yeah, I have it, so it's going to be very easy when I do it. Perfect. Cool. Perfect. Excellent.
Awesome. So I want to start, as always, by not talking about the paper, but talking about you, because this is also an excuse for me to ask questions that would be weird if we were just hanging out and doing something. So I think I remember meeting you at NetSci in 2007, which was one of the first NetScis. Is that possible? Running around?
Was it the one in Italy?
No, it was the one that was somewhere in Britain that wasn't like.
Oh, no, indeed, yes. So it was actually, it was in 2008 then. Or 2007, whatever. Yes, it was in this, it was a strange location, because usually they have us having these meetings in, well, wonderful prestigious cities like Venice, like Paris, and there it was not in London. It wasn't in Cambridge or Oxford. Wasn't it in Norwich?
Norwich, yes, that sounds right. That sounds exactly right. I'm good.
Yeah, actually, and I remember that actually it was also it was the first time I met you. It was also the first time that I met Jure Leskovic. I remember, because I was in the same bus as he was. So there was a bus somehow to either to go to the conference or to go to the hotel, and I was sitting next to him. And I remember that that NetSci was the first time I presented this Louvain method, and I was very nervous because my English, I wouldn't say my English is perfect now, but my English was not as good at that time. And so I practiced a lot the night before, and the room was packed. I think it must have been the one and only time that I felt as some sort of a rock star. There were like plenty of people in a small room, including Mark Newman at some point. Oh, and so having Mark Newman in the room, well, I didn't know what to expect. No. And actually, I was happy that he was there, because one of the questions at the end, I didn't know what to reply. And he was the one who gave a response. He said, I think that someone said something about, well, but this is just a heuristics. You don't know that he's going to be providing the right answer. Well, you can only say fair enough. And then I remember that Mark Newman saying, interrupting and saying, well, I've been doing that for many years. Well, there is no true answer in any case. So this is a heuristic, but a very useful one. So I felt like I had to receive somehow the green light from the prestigious Mark Newman, which is a very good feeling.
Yes, very nice, very cool. And yes, I remember being also petrified of him in the audience at some point. He was so prolific in the early days of network science.
And also he's the one, so I didn't do my PhD in networks. I arrived in networks after my PhD, and I remember that the paper that I would read and reread in order to discover the field was his excellent Science Review paper, the one of 2004 or something, which is a book of its own. And actually, I still give it as a reference to students when they start. So, of course, it's a bit outdated for certain aspects because it's almost 20 years old. But nonetheless, there are so many good ideas and intuitions in it that it's still, I think, a very nice and intuitive way to go into the field.
Absolutely. And I think also the book that he wrote later, the textbook, kind of has the same structure. And it's basically a kind of a vastly expanded version of that paper almost. But yes, I read that many times. There were kind of some. There was also Renaud Albert's review paper that was also kind of a really nice overview. But so now you mentioned that you didn't start out in networks. So how did you even arrive in science? I check. What I do now is I go to the Google Scholar and I sort things, I guess, anti-chronologically, and then scroll to the bottom and look, and you have a lot of papers about all kinds of things. So how did you even like get started in science? What did you do your PhD? Can you talk a little bit about that?
Yeah, of course. So since I was a kid, I loved math in a broad sense, and also physics, because it's the science that would be the closest to math. But I didn't have like very ambitious expectations in the sense that when I started my studies, what I wanted to do was to become a high school teacher. And that was really, well, my parents were teachers, my mother was a teacher. So in my mind, I would study physics and I would become a physics teacher in a high school, which is something that is a wonderful job, obviously. And then I studied, and actually I remember that at the end of my fourth year, I actually followed all of the lessons to become a teacher. But then a professor came to me and told me, well, why don't you do a PhD? And I was extremely naive. I roughly knew what it was, but I wasn't quite sure, actually. So I think that even the word PhD, I didn't know it. It was a doctorat in French, but the word PhD, I wouldn't know it. Yes. And I said, oh, what is that? Oh, but you get a salary to study for 4 years. And it seemed like a dream, right?
Yeah.
So actually, I applied for a grant, but it was kind of a funny thing because I applied in September. And I would only get the funding. I would know if I get the funding at the end of December. And if I got it, I got 3 months in one shot. Yes. And so I started my PhD, and luckily I got the funding. So it means that in December, I was rich, nice. Beyond any dream that I may have had. 3 months of salary, like the glorious salary of a PhD. That's and three months in one shot. It was wonderful. So I guess that I invited some friends for a drink, possibly. I bought a computer. I remember it was one of my first computers, and then basically I did my PhD, and my PhD was on the topic of my master dissertation. So I studied physics, and it was I studied physics in Brussels, where there's this school that comes from the works of Prigogine. So actually, Prigogine is I think my grandfather, if you look at this kind of like the promoter of the promoter of the promoter. No, he's my grandfather, actually. So yes. My promoter is Léon, and the promoter of Léon was Prigogine. So I was completely within this kind of school about statistical physics, irreversibility. How do you explain that things are irreversible at our scale? But if you look at atoms, the dynamics would be Newtonian and that would be reversible ones. And I did my PhD on something that is called granular flows. So you take grains, you shake them very hard, and then all of the grains move around a bit like atoms. And except that every time they collide, they would dissipate energy because these are macroscopic particles. And so it means that if you want them to continue, unlike a gas, you need to sustain some energy into the system, to provide energy to the system, and it is going to be moving like in a fluid way.
Yep.
And I was trying basically to study something called the Boltzman equation for inelastic gases, and from there to write some hydrodynamics and also to do some simulations. So I had something that was a bit between simulations and theory.
Really cool. This triggered also a memory for me, which is I also don't come from a family of academics. And I also remember exactly this thing that when you're starting out, you don't really know the order of things. So I also kind of found it, you know, like you start out at university and you're like, okay, university is what you do. And then as you're kind of approaching the end, then there's someone who's like, there's something called a PhD that's pretty cool. And you figure out about that thing. And then as you're doing a PhD, you're like, oh, there's something at the end of this called a postdoc. And I had no idea. And at every level, there is this kind of
there's this surprise. And actually, I think I use the word naive, which is said in the positive sense, right? So my whole career, I don't think I had many plans. So, and I've been lucky in some ways. I guess I deserve something, but I was also very lucky through the meetings I had, through all sorts of chance that you have in your life. Yes. But I didn't really plan to finish at university. I enjoyed it. I continued. I had the chance to meet the right people, to work with them, to collaborate. But I know that I'm so surprised these days when I meet students. Many of them are extremely well prepared, and so they can write statement of research. I think that's a few years back, I found back my application that I wrote to get my funding. And it was still at a time when I had to type it on a copywriter. I couldn't do it on the computer because it was a special paper, a green one, very thick. It wouldn't go into the printer, and so I had to print to do it the old way. And of course, every time you make a mistake, you take it out, you start again. So it was just writing one page took me 2 days just because of the impossibility to erase anything. But it was completely unprofessional with respect to the science that I see now with students. Now, students, even for master, when they apply, they have a vision. Well, I don't think that I had a vision at the time. I just enjoyed it, and that was what's driving me.
Yes. No, I completely also recognize that thing. Like, first of all, I like you, I was also kind of at every step, I was also thinking high school teacher seems like a pretty great gig. And that's what kind of makes sense after studying physics, which is something that I love. And then at every step, I was kind of like, well, I'll give it a shot, see what happens. And I think so I recognize my own path in yours, but I wonder if that's also possible now, because things are also changing structurally. Maybe the kids are well prepared because they have to be. I don't know, but it was definitely, I was also not very driven.
No, and so I agree. I think that now things are becoming more and more professional at a very, very early age. And I know that, well, so I said, so I did my PhD, and actually I did it for a bit longer than I should, because my PhD, I was given the luxury to have no pressure and to have a very open project.
Yeah.
And this is something that is dangerous, because I lost my way many, many, many times. But at the same time, it taught me to search, right? So I learned to search and to try to find questions. And most of the time, the questions were stupid, and or the solutions were wrong. But at least I learned by trial and errors, and I really learned a lot on my own, which is actually, so I thank my advisor a lot that it gave me a lot of time. He didn't advise me much, but as a parent somehow, well, when I was really in need, he was there just to comfort me, to say, well, please don't stop. let's give it another try.
Yeah.
Come back in 3 months. We'll have another chat and we'll see what happens by then.
Yeah.
Or I have a break of 2 weeks and then but really having this kind of freedom was a wonderful luxury. And actually I spent a lot of my time when I did my PhD just to procrastinate, just to think and to read. I remember that I was, so as I said, I had something related to the Boltzman equation, which is this very famous equation from the 19th century. And I was really fascinated by it. And it's a really beautiful equation. And I read all papers of the 19th, of Clausius, of Boltzman, of Ehrenfest a bit later on in the 20th century, and had an old book with translations from German to English of the original papers that were commented with more like some more modern thinking. And I remember that I spent a lot of time just to read and to build my culture somehow. And today it wouldn't be possible because, well, I had a great time, even if it was difficult at some points, I guess. But at the end of my PhD, I had done 5 years and I had published no paper. So it means that I finished my PhD with 0 papers. I had gone to 3 conferences, and the first one, my presentation was completely wrong. And I wouldn't say I was insulted, but I was really brought back to my place by a more senior researcher who just told me, this is nuts what you presented, and he was right. This was completely wrong. But yeah, that's you learn by your mistakes, I guess. And so when I finished my PhD, so after 5 years, so I had some results, obviously, but nothing published. And then comes the time of the postdoc, the famous one that you mentioned. And actually, at the time, so I defended, I think, in June. And I had funding until the end of August, I remember. And so when I defended in June, so someone from the jury actually had possibly, wasn't sure yet, an opening to study at the University of Liège, which is a small city in Belgium, in a European project called, it was called Critical Events in Evolving Networks. So It was some sort of thing where like the interface between statistical physics and network science. And I didn't know much or nothing about network science at the time, but he wasn't sure yet. So I remember that I applied to become some sort of like an engineer in a center where they were like modeling diamonds. And I went to Antwerp, and they looked at me, they looked at my CV, they say, well, very good, but, and I explained to them, oh, there are all of these wonderful simulation techniques, like ab initio, and so, no, we don't want that. We just want something where you use MATLAB, and they didn't take me, luckily. So, and so luckily, well, the things that there was this postdoc position opening in Liège, and so I started there, and that's when I started to read the book, the review paper of Newman, and that's when I started to go into that field.
Yeah, and I guess just looping back to one thing, which is you talk about this exploration, and I think it's important, and it's also, I kind of want to come back to that also in the context of the paper you'll be presenting, because I really think that there's this thing about that ideas grow from ideas, and this thing when you have a research plan, a lot of times when it's research, you don't know where it's going. And I don't know about you, but I feel that all the really good ideas I have had, if I've had any in my own estimation anyway, the ideas that I think that I like have come from some other problem that I was working on. So you work on something, you bump into an edge of the problem, and there's something weird, and then you realize, aha, this is where it is. And my sense is you can't plan those. The kind of the big things, they come at you from bumping your head up against nature or the thing that you're investigating.
Yeah, no, completely. And usually it comes from all of the culture that you've been growing, right? And the kind of vision or the landscape, the vision that you have about the research landscape. And indeed, so as I said during my PhD, I read a lot, and sometimes papers that were completely irrelevant because they were like things from the 19th. But nonetheless, I read a lot about entropy, a lot about like the emergence of order in systems. Yeah. Even I read a lot about timescale separation, because when you go from the microscopic to the macroscopic world, somehow well, you have conservation rules, and so you have some sort of time scale separation between some slow variables and the fast variables.
Yes.
And these are all things that are extremely important concepts that I've been continuing to use afterwards. So when I looked at networks, community detection, for instance, well, part of it can be phrased in terms of time scale separation, the large the things that are extended in space versus things that are very local in space, the slow versus the fast variables.
Yeah.
And this is still something that is at the back of my mind and part of my education. And I didn't learn that it's in the lessons. I learned that by practicing and also by reading stuff from different disciplines.
No. I remember that paper. That was from another NetSci in 2009.
Just a bit later.
Yeah.
No, but I fully agree that indeed, like the good ideas, I'm not against writing grants. So, because actually sometimes writing the grant is part of the process, because when you write a grant, or if you write a report, I just had last year to write a report because I'd been for 3 years in Oxford and they wanted to evaluate me. And so you take a step back. It's a bit annoying because you would like to do something more playful. But nonetheless, you take a step back and you think about what you've been doing, and you write what are your accomplishments, or maybe the ones that you would like to do in the future. And of course, well, sometimes there are a few empty sentences that you use, but nonetheless, you are. I think that it's a time when you somehow think about the broader direction where you want to explore, and it obliges you to do some reading as well. Because, as you said, like new ideas come from existing ideas, and I think it's really the first advice that I give to my students is that, especially at the time they have a lot of time, so please read as much as you can, right? And I will not complain if next week you come to me and you tell me I didn't do much because I read 5 papers. Well, that's wonderful. What did you read? Can you explain something to me? And I think indeed, like when you write these grants, well, part of it is a bit of a futile exercise because you have these work packages and you say, well, I'm going to do this by using that method. And possibly, yes. But nonetheless, it helps you somehow to build some of the bricks. And it could be that at the end, the bricks will lead to something different, which is, this is the way science happens. But it obliges you somehow to think occasionally about the direction that you want to take. And I don't apply to grants very often. Here, I did it for the first time in 3 years last year. Yeah. So I try to do it once every 2 years just to get the sufficient fund for a postdoc, but I'm not a serial grant writer.
No, I mean, with the grants, just spending 2 minutes on this, I agree with you, but I just find it very, very painful somehow. I don't know why, but I find it so difficult because I like exactly the tangible and the concrete. And as soon as it becomes, I want to go in this direction, and now I have to fill in the details of the direction I don't really know. I agree that it helps me, and I agree that how else can they hand out millions of euros or dollars for our international listeners here, or probably many other currencies.
Yeah,
I said international. This is like the least international, I guess.
I guess not millions yens, because it wouldn't it wouldn't be much.
I don't even know about the exchange rates. I feel like I'm getting in trouble. They're going to cancel the podcast immediately if we don't stop talking about currencies. No, just kidding. But anyway, how are they going to hand it out if you haven't thought about it? But I do find it much more difficult than anything else. To me, it's the most kind of uncomfortable, painful way, because I'm feeling that I'm somehow, I don't know, being disingenuous, and I like that I can put somehow weight in every word, or that I can mean every word that I write.
Yeah,
it feels somehow.
I try to be as honest as possible, but well, especially for the reviewers, if they listen, obviously.
Clearly, yeah. I mean, answering reviews is another genre that we could talk about for a long time. But let's move on. So you're getting into networks, and again, when I look at your publications, you've been super prolific. You've written about many, many topics, not just networks, but also like any good physicist working in, you know, getting into other people's disciplines. But a big kind of flow through your work came out of the community detection. And by the time when we were kind of come out, we were both working in this area, and there was this big, the fast unfolding Louvain paper that you wrote, that you talked about. But then there was a lot of kind of refinements and going deeper with that. So why was that interesting? Was that because there was a lot of cool math to be discovered, or?
Yeah. So indeed. So as I said, so my PhD I didn't write papers, and then I discovered like the true, well, the reality that this is something that would be expected at some point. And indeed, like in the first 3 years, in my first postdoc, honestly, I learned to write papers, and I wrote many. Yep. Many of them are not so good, but I learned basically also by practicing.
Yes.
And that's also how I discovered the field. And some of the papers I wrote at the time, I look at them and I'm like, oh my gosh, man, what did I do? And especially because, as you say, I was a physicist doing social science somehow, and part of it was done in a fairly, like lousy way, without like properly like engaging with the literature of their field. And that's something that I learned along the way. But then indeed, like, so so a lot of the work that I did, I think between 2008 and even until now, actually, well, that's really been about this question of like different scales in systems.
Yeah.
And when I started, actually, so the Louvain method. So I arrived in Louvain in the group of Vincent Blondel, and actually they already were starting working on that when I arrived. And so I arrived in the project that they had started, and so we worked on that. And actually, it's been a very, very efficient project that we tried to submit to big journals. I remember we tried Nature and Science, and we went down the road. And then after it had been rejected by everyone, I said, well, let's submit it to a physics journal. And we submitted it to GStat, which is the Journal of Statistical Mechanics, which is probably not the most famous journal, but it was a good one. And I liked it because it's a journal where at the time, as a referee, you were paid 20 euros as a referee, which I found like a very, very nice gesture that they had for their referees.
Yes.
But and indeed the things that, so initially it started more from this kind of algorithmic point of view, like how do you find these communities and how do you optimize modularity? And actually I'm not so in statistical physics you have two schools somehow. You have the people who are interested in equilibrium statistical mechanics, and then you have those that would be more interested in the non-equilibrium ones, like and about like statistical mechanics system that is not at stationarity, it's evolving in time. And the thing is that the Louvain methods and modularity optimization, more broadly speaking, it relates more to the first type, because you have like some sort of a spin glass and you try to optimize to find the ground state, and this is something that is very much related to some type of statistical mechanics that I didn't know so much, actually. So I had to learn a lot, which is fun, obviously. But then after that, actually, after that paper, so I changed group. I arrived in Imperial College in London, and I continue to be interested in this kind of like presence of communities that would be inside networks. Because indeed, I was fascinated by the fact that when you have a graph, a network, well, most of the models that you have, you can think of Barabasi-Albert, Adorshani, whichever you wish, they tend to be, well, heterogeneous for the degree of distribution, but homogeneous in the sense that you have one big group of nodes, and they form some sort of like an homogeneous set of nodes, right? While in practice, you tend to have all of these clusters that are present in the system. And I was really fascinated by what would be the mechanisms that would lead to the emergence of these types of structures, and at the same time, what would be the impact that this type of organization would be having on the functioning of the system. Yeah, and that relates again to the Newman paper, right? The structure and function of networks. So we see that the graphs are organized in a modular fashion. what would be the mechanism that explain this kind of ubiquitous organization, but also what would be the impact that it has on some dynamical process? And the simplest one would have been random walks.
Yes, but and that's also what I thought is cool, right? So just for whoever is not really into statistical physics, this paper got huge, like really enormous, right? And I think I just checked, and it has almost 14,000 citations.
Yeah.
And part of the success is because it was you made the code open source so everyone could go and get it, and it was made available in C and Python so you could run it, and also because it actually did, like Newman said, it was a really good heuristic, right? And I think some of the cool parts of your work is that later on you've also done work to quantify actually how good it is, connecting it also to some of both, like you said, to the timescales of what you're optimizing and understanding the quantity better, but also connecting it to InfoMap. And so there's a lot of beautiful work kind of following up and actually anchoring this, which was and still remains a fantastic tool for a network scientist, right?
No, and the thing, yeah, and so the thing is that we are lucky also to have a fairly interdisciplinary team. So I know that the original idea came from Vincent. So Vincent was, I think, on sabbatical in the US in 2007, I think. I don't know, I think he must have been at MIT, but it was the time when I think he got to know, he was confronted to this problem of modularity optimization. And he thought, well, there are some tools that exist, but he thought that there was a way to do something better. And at the time, there was a very nice heuristic as well, the one that was proposed by Klose and Moore and Newman, actually. Yeah. And it had a good idea, but somehow in the way it was implemented, it somehow had a problem because it led to some sort of imbalance. By the way it was created, it tended to find communities that would be some very large and others very small. So there was something that would be having to improve on that. And in a way, Louvain is really like a next step on this CNN algorithm that is a bit older, and that partly allows to avoid this kind of emergence of imbalance. But indeed, as you say, so the things that, so we were a team where there would be applied mathematicians, Vincent and Etienne Lefebvre, who was a student, me as a physicist, and there would be Jean-Loup Guillaume, who was a computer scientist. And so, and indeed, like the fact that the code was running well was because it had been properly written by a computer scientist.
Yeah.
And so we had this kind of like interdisciplinary team. And yeah, it was a fantastic project. And as I said, it was very difficult to publish, extremely difficult, but it took us a year to make it accepted, which is long, right? But after that, yeah, it's been successful, and partly because it's a very simple idea. So the algorithm is very simple. I teach it to my students, and the algorithm to explain it takes about 15 minutes, I suppose. So just the big ideas. So it means that it's very simple to understand and nonetheless relatively efficient. You can improve on it. You can use the Leiden method if you want. That is a way to avoid certain side effects that you don't want to have from Louvain. But nonetheless, it remains a fairly robust technique that people use. And yeah, so it's I know that it's a paper that represents more than 50% of all of my citations. So I hope that the people are going to continue to use it. Otherwise, my citation rate is going to be going down quite drastically.
Yeah, don't worry. I still recommend it in my class as a good way to do community detection. So I'm doing my little part to help.
Wonderful. Yeah, because I was preparing to have my T-shirt on use Louvain method, please, but I forgot it and I use my colorful shirt instead.
Yes, well, I'll make sure to somehow put it in the show notes that if you want to divide a network into pieces, this is a great way of doing it. Awesome. But maybe we've already spent a lot of time. I wanted to spend a lot of time, so it's not in any way a problem, but maybe we should get to the paper that's too lazy to read. Yep. So let's, I have it with me here, and it's called Variance and Covariance of Distributions on Graphs. So you can already hear that it's connecting to all this stuff that you've been telling us about, I think. But how? So I guess I guess I have to ask one more question before we can get started, just to create continuity to what I was saying before, which is, as you start to tell about it, we know now that all the great ideas come from other ideas. So how did this paper come about? What's the story in the context?
Yeah.
Before we do the content.
No, actually, this project started from a question that someone asked me. And so it started a long time ago. So Michele Cosia, who's actually a colleague of yours, if I'm correct.
Well, he's in Copenhagen. And
yeah,
as you know, great data science environment in Copenhagen. So many cool people have arrived here recently. So he's here, but he's at a different university. But I do see him.
Okay, well, I give my greetings. And so actually at the time, so Michele had been a postdoc of mine, or somehow a postdoc of mine for, well, it was, he got funding, but well, in any case, it's a complicated story, but he was a postdoc of mine for some time. And Michele was very much interested in this atlas of economic complexity. This is something that he's been working on in Harvard. Yeah. And I remember that he came to me because he wanted somehow to quantify what would be the diversity of the economic activity of a city. Mm-hmm. And if you want to, I just have one image I could share to the people so that it's easier for the people to see what I want to talk about. So let me just join the meeting with my iPads. Launch the meeting. Okay. Join without video.
Yes, your iPad is joining us.
Yeah, wonderful. And then I'm going to be sharing my screen. Yeah, it should be working, hopefully.
Let's see. Yes, we're seeing it.
So far, so good. And then, yeah, wonderful. So this is just like one picture that is taken from this atlas of economic complexity. And this is something which they call, if I'm correct, the product space. Yeah. What they have with this product space is that each of the nodes would be a product that a country could be developing. It can go from, I don't know, like beer to ping pong balls, I suppose. Yeah. And here what you have is like you have connections between the products. Yeah. Depending on some rules, the fact that two countries would be exporting them together. But in any case, you have certain relations that exist between different products, between different types of industries. And once you have this product space, the question that he asked me was, okay, so he has this product space. He knows that a certain city is active in certain industries, and another city is active in other industries. And the question that he asked me was a very simple one, is how do you say that one is more diverse than the other one? Yeah. And in a way, the kind of question that he had was, well, let's assume that you have a country that is active in this area, right? And maybe this one as well, for instance. Yeah. Yep. And another one that would be active in this one here and that one there, right? Yes. So, and you basically have that, okay, so you are active in certain regions of this space. How do you quantify somehow the diversity of the activity? And he wanted to use that as a way somehow to characterize the economic activity that takes place in different cities and to compare them. Yeah. And the question he asked it to me, I think it must have been 6 or 7 years ago. And I don't know why. I remember that I found the question interesting, but I remember that I didn't have enough time to think about it. It could have been because I just had a baby, possibly. That's the good excuse, I suppose. It must be that, or I don't know. Something came up, and I remember that the answer that I gave was okay, but it was not very not very deep. I say, well, what you could do is you look for communities. I was probably in a phase of my life when I was obsessed by community detection. You divide the network into communities, and then you compare the vectors of the vectors that you have inside for inside the communities for the different cities. And if you have a vector that is very homogeneous for one or very peaked in the other, well, the one that is very peaked would be very concentrated in terms of activity, and the one that would be very, very flat would be one that would be very homogeneous. And I think that's, well, and I stayed there. I didn't think much more about it. But nonetheless, I kept it at the back of my mind, because this kind of question is something that you can observe in many systems where you have a graph, right? And on this graph, and this graph tells you that you have variables, and these variables are somehow related with each other, yes? And you may have a distribution that is defined on this graph. Yeah? And somehow the question that you ask is, how concentrated is the distribution? Does it tend to be like, is it peaked in nodes that are very close to each other? Or is it something that is very much spread across the whole system?
Yeah, so just to kind of rephrase and make sure that I'm, you kind of, you're working in the space where you don't just have links and nodes, but you also have the information about each node. And then the question is, when you have a network structure, it's easy to kind of define, and, you know, like if you have, well, it's not easy, but it's easier to define if you have a very well understood structure, a grid or something. But once you have a network and you have properties spread out across the nodes, how do you somehow measure how spread out it is? Is it all concentrated, or is it something that's a property of every single node you might run into?
Yeah, no, exactly. And the thing is that when I try to think about that question, I remember that, so there are extreme cases where the answer is known. So, and very well known. So if you have that your variables are organized in a matrix, in a Euclidean space, yes, then you can simply use the measure, the variance, right? You measure the variance, and the variance is a measure of how spread is your distribution inside that Euclidean space. And this is something that first your students know. So, and indeed, when you want to measure the spread of a distribution in a Euclidean space, well, the variance makes the job extremely well.
Yes.
Now, there is another extreme, which is quite different, is in the case of categorical variables. If you, let's assume that you have different categories, but they're not connected with each other. You have categories. Then a simple way would be to take the Shannon entropy. Yeah. And the Shannon entropy, again, will tell you that, well, the entropy is going to be high if you have something that is very homogeneous, and it's going to be very small if you have something that is peaked in one single variable. Yeah. And in a way, I was interested in what would happen somewhere in between, right? Where you don't have like a completely regular organization, as would be in a lattice, where you have the distance that would be the Euclidean distance. But you get something where the structure has you have a complex structure, right? A complex network. Yep. You have certain variables that are maybe very much connected with each other. You may have clusters, you may have groups of variables that are forming groups, and so therefore they're somehow equivalent in a way. And given the distribution that you define on that, how could you somehow define the spreading that it has?
Yes, no, absolutely. It's a really interesting question, and the first description you gave to how you suggested to Michele to calculate some metric of this variance was exactly also reminded me of the entropy. It has already a little bit of an entropy.
Yeah, exactly, because indeed, like if you define a vector that is coarse-grained onto your communities, right? Yeah. But then you have a vector, and that vector, you can normalize it to get a probability, and then you can use like Shannon entropy, for instance, in order to quantify the diversity across the different communities that you've been finding, basically.
Yeah. And zooming out, I think it's also really cool that we're beginning to have tools like this on networks, because networks exactly are these very in-between things, right? We have distances, we have path lengths, but they're very different from distances in the kind of spaces that we know otherwise, right? So what does it mean that something is, I mean, yeah, like how do you define the complexity of a corner of the graph, right? If we look at the picture that you have, we can see that up in some of the corners, the graph seems somehow more simple up there, not just in the one-hop neighborhood of the node, but in this area of the graph. And you see that maybe other areas have different seem like there's a lot of links and a lot of things going on, but we don't really have good measures for the complexity or the, I mean, that's a kind of overkill to use that word, but even for the, like these differences in the various corners and areas of the graph. So this also is interesting because it's something where we don't have so much of vocabulary, because the distance is either, like you're one step and it's kind of too close, and then you go 2 or 3 steps and then you have the whole graph. And so these short distances make it difficult to define local complexity in the corner of a graph. Does that make sense?
Yeah, no, completely, yes. And that's actually related to the fact that sometimes like shortest path distance might not be the most appropriate measure of distance. And actually, I was planning to say just something about it. And but indeed, like, just going back to this kind of two extremes, right? In a way, if you think about like a graph with two communities, right? Mm-hmm. When you have two disconnected communities, what would happen is that actually, indeed, like all of these variables here are equivalent, all of those there are equivalent. But then if you start somehow to make them connected, well, they start to be somehow connected with each other. And the problem becomes a bit more difficult to properly define what would be the distance existing between the pairs of nodes.
Yeah.
And I remember that, so I had this question at the back of my mind, and then a few years later, I started to work on a project that was completely different. So we collected data from the archive. And what we did was we've been downloading the source file of all of the text files that can be downloaded on the archive. And the initial idea was to try to extract equations and to try to find some semantic relations between the equations. And we started, but we never finished. So maybe maybe in a few years. But then we did something a bit simpler. What we did was we went on Wikipedia, and on Wikipedia you have a list of theorems and equations and methods, like a Fourier transform, like I don't know, like the wave equation, and so on and so forth. And what we did was we had like a list of concepts, mathematical concepts that were taken from Wikipedia. We search for them inside all of the papers, right? And so what would happen is that each paper would basically have a certain number of concepts that it has, right? Yeah. And it would be something that characterizes the paper. But on top of that, of course, on Wikipedia, you have some link you have some web links that exist between all of the pages of all of these concepts. And it could be, for instance, that the heat equation and the Fourier transform will be connected because one has been devised in order to solve the former. Mm-hmm. And so it means that you have relations that exist between certain mathematical tools. And it means that what you have is, on the one hand, you have a graph of concepts that are related with each other, right? Yeah. And on top of that, what you have is a large number of papers, and each paper basically has a certain set of these concepts that is associated to it. Yes. And I remember that when I saw it, I thought, oh, that's the same problem as the one that I just said before, right? Because instead of having a network of products, I have a network of theorems or mathematical concepts. And instead of having cities, I would have papers. But nonetheless, this is roughly the same kind of idea. And so I was, well, that's maybe the time to think a bit more about it. And I was lucky that, so I worked on that with a student visiting from Spain, Samuel, but we talked, and then I said, oh, maybe you could have a chat with Karel, and Karel is a PhD student of mine, because he's working on this effective resistance, and which is like a nice way to measure distance between nodes. And maybe there might be a way to combine these two projects together. Yes. And then I think that's 2 days later or the next day, Karel came back to me and said, oh, I just found something funny. And so basically what he found, and I just write it down for you here, is that, so if you have a certain, well, I'll do it in black, it's going to be easy to do. Yep. So if you take a certain distribution P and you calculate what is the variance of the distribution, right? Yep. But he said, well, let's define the variance as this. So you have 1/2, and then you have a sum of all pairs of nodes. And then you have P of I, the probability that you observe state I, P P of j, and then you have the square of the distance between the two nodes. Now, this is here a very general formula, right? So what you say is the following. So I have a distribution P that is defined on all of my nodes, right? Mm-hmm. Let's assume that I have a certain measure of distance between any pair of nodes, right?
Yes.
Then I will define my variance as this quantity here. And so basically what you do is you look at all pairs, right? And you look at the distance that they have and you verify whether or not basically what you have is that if Pi and Pj are large and that the distance is large, it basically means that the variance is going to be very large. So it means that if you have nodes that have basically very high values of the probability, but that are very far apart inside the graph, that would actually lead to a measure of the variance that would be a very large one. So it seemed to be somehow intuitive.
Oh, it makes a lot of sense.
And the thing is that what is nice further than that is that actually if you have that your nodes are actually on a lattice, yes, and you define your distance to be the Euclidean distance, then actually that formula is exactly the same as the variance that you learned from school, which is the average of x squared minus average of x to the square. So it means that you recover the standard measure of variance in the situation where you have a lattice, a Euclidean space, and you use this the Euclidean distance in order to measure the distance between the nodes. So it means, at least in this classic scenario, that seems to work perfectly well. And actually, something that
network also on the network, it is a very intuitive distribution of variance. It kind of fits with your intuition about variance, right? Like, so in that sense, not only does it fit, but it is a very natural question here for the network.
And actually, something that's I'm not sure it's correct. We just figured out a couple of days ago was that actually, if you have a system that is such that you have your distance ij is equal to delta ij, so it means that you would only or 1 minus delta ij. So 1 minus delta ij, meaning that I and j are at ii is at distance 0, right? Mm-hmm. But other than that, any pair of nodes is at a distance 1. Actually, in that case, you can see that this expression that you have is going to be related to something called the Renaud entropy. And so it means that if you have a situation where when all of the nodes are such that you have some sort of categorical variables that are defined in your system, mm-hmm. What will actually happen is that you recover this kind of other extreme, an entropy, maybe not the Shannon entropy, but you find the Renaud entropy. That is also something that is known to be a good way to measure the variability that is present inside your system.
Yep.
And so it means, and indeed, like from a network perspective, it perfectly makes sense. Now the thing is that when you have a network, then it comes the time of a choice, right? Because here you need a distance. And typically the measure that most of the people would be using for the distance would be the shortest path distance, which is a very classical one. But one issue that you raise is that for the shortest path distance, well, first of all, it tends to be defined over a very small set of values. Yes. Because the graph are small world. So it means that typically after a distance of 3 or 4, you reach basically, you go from one extreme from one side of the graph to the other side of the graph, which would be a first problem. And also something that is well known is that the shortest path distance is a very fragile measure, in the sense that if you add some noise by removing randomly a few edges or adding randomly a few edges, you can drastically change the distance between two nodes. Yeah. And so that's why it's one of the reasons why instead of looking at the Euclidean distance, what we did was to look at this effective resistance. And initially it started from this argument, but also because Karel was very much interested in the effective resistance. And also, I suppose as a physicist, I loved electric grids when I was a student. I just found it that the Kirchhoff laws are just wonderful. And what is the effective resistance? Well, actually, the effective resistance is a concept that has been in the literature for quite some time. And it basically sees the graph as a big electric circuit, right? And then you say that what would be somehow the relation between two nodes, it's going to be somehow the effective resistance along all of the path that would be going between these two nodes. Yeah. And this is a measure that has wonderful algebraic properties, because you can calculate this effective resistance from your Laplacian. And I love the Laplacian because the Laplacian is related to random walks, and I've been doing a lot of stuff on random walks on networks. And actually, you can actually formulate this effective resistance in terms of something that is called the commute time. So when you have two nodes, right, this effective resistance that is understood as the resistance between two nodes along all of these parallel paths, right, yes, can equally be formulated in terms of random walks as the time that it takes to go from one node to the other one and back. Yes. And this effective resistance slash mean commute time is actually something that people have been proposing a lot in an area of network science that is related to embeddings and the definition of kernels and distance measures between pairs of nodes, where what you try to do somehow is, yeah, you start from a discrete system, yes, because the graph is discrete, and you try to go somehow into a continuum. For instance, by trying to embed your nodes into a metric space.
So it's super cool that we're bringing this kind of up to date and to embeddings and all the stuff. Kirchhoff to embeddings is cool, but just a curiosity. I mean, in some situations, this measure would still be fragile in the sense of adding a link to the underlying graph could still change it a lot, right? Like if not in all configurations of the graph, but in some configurations, you could still imagine that like a very similar fragility. Is that right? Or
actually, I will probably say something wrong that I'm going to be writing tonight when I don't know exactly when you're going to be putting this online. So so please, if I call you later this afternoon and say erase this, you should erase it. Right?
We'll cut it out. Cut it out.
No, I'm just the thing is that indeed I can envision situations where indeed adding an edge will change drastically the effective resistance between two nodes. But nonetheless, the thing is that so the effective resistance can be calculated from something that is called the pseudo-inverse of the Laplacian. Mm-hmm. And I think that's from the fact that the spectral properties of these of the Laplacian matrix is somehow robust to noise, in the sense that if you add a tiny deviation, it will not change too much either the eigenvectors or the eigenvalues. I would expect that it would also mean that the effective resistance, except if you have two nodes that are not connected at all, right? Then of course you add an edge, it's going to make it, it's going to lead to a drastic change. But otherwise, if the graph is connected, I would expect that a tiny change, the addition of weights, one edge with a small weight, shouldn't affect too much the effective resistance between them. But I may be wrong. So that would be something that I should.
Makes sense. It makes a lot of sense, and probably you can construct, like you said, you can construct maybe like if you start from, let's say, like a Watt-Strogatz situation of not like a grid with some very long paths, and you add shortcuts, you could still see something. When like artificial situations, but I get that in general. I'm sure you're right also.
And the thing is that so in general it is clearly more robust than shortest path distance. So that would be something that is clear.
And away from embeddings. So sorry about that.
No, that's fine. And the thing is that one very nice property. Well, first of all, it connects to random walks, but also the thing is that because everything can be expressed with a Laplacian, it means that algebraically you can do a lot of work on the effective resistance and calculate it, and also sometimes derive some mathematical results that would be in a more easy way than you would do with the shortest path distance that doesn't have this formulation in terms of matrices. Mm-hmm. And so basically we started on that, and so basically, okay, just an example here, right? So here you have a graph, a single graph, right? And what we do is we define a certain probability on the nodes, right?
Yeah.
And here you have different configurations where the graph is the same, but you have different ways in which you assign your probability on the different nodes. And you also have the measure of the variance calculated from the way that I just said before. And indeed, it seems to be fairly intuitive that, well, if all of the probabilities not assigned maybe on a single node, but on nodes that are very close to each other in the graph, well, the variance is small, right? Well, here you have something where you assign it to nodes that are very far apart of each other, and then the variance would be a very large number. So it means that indeed, it seems to capture this kind of intuition of the locality of your signal that would be defined like somehow locally inside the graph. Which means that at least like from these few examples, it seems to be working fairly well.
I really like this. I really like this for a number of reasons, but and maybe it's too deep to dig into because we've already spent an awful lot of time talking, but I think this is really cool, and it's something that's very also usable. It's something that we kind of need, right? But one of the things that drove me always crazy was when you look for communities in networks and you were comparing with ground truth data, and then you would compare kind of your labels with your communities, right?
Mm-hmm.
And then and so you divide the graph into some groups, and then you also have some labels for data, and then you could then calculate the mutual information between the labels and the groups, or whatever you wanted to do to compare the overlap between the communities and the labels. But what I needed was I always wanted a metric of the variance of those labels, because you could kind of imagine, like let's say men and women could be a label, but clearly that's one that has high variance in the sense that it's categorical. So I know it's not quite what we're talking about, but it's very distributed across the graph. Yeah. You could also imagine kind of a label. Let's say that you have something that's very concentrated and is only present in one community, like a very community-like label, which would have a low variance in your world. And you could also have something that was in between. Like you could have people playing together. Actually, that would also have a high variance. You could have like bands, for example, and then you could say, you could have a lot of people that play in a band together, and those bands would be highly clustered on the graph, but they could be distributed everywhere on the graph. So it's just one example of where if you could quantify the variance of those on labels on the graph, you would see that some of them are very community-like and it would have low variance, and some of them are very non-community-like and would have very high variance.
Yeah, no, yes. And actually, that's something that's...
I wish I had...
We didn't explore completely was how does this relate to assortativity, right? Because indeed, because assortativity is a very local measure. What you do is, given certain attributes, well, you just look around pairs of edges, and in a very, very local way, you try to estimate if there is some sort of like a correlation existing between them. And somehow it's a very local measure of localization in a way.
Yes.
While here we're interested in more globally, like one number that would be telling you, that's something that's clearly we should investigate further. And something that you might like, actually, because I will not talk about it today, is that we can measure variance, but we can also measure covariance. So it means that you can also then, because of that, take two distributions and try to find whether or not the two distributions are the same or different of each other, which might indeed be something that we didn't really do for that, but could also be useful in the case of community detection, I suppose.
Yes, but I mean, covariance on a network, I think, could be interesting for so many practical applications also, right? Which quantities covary on a graph. And of course, there are many kind of ad hoc ways of measuring it. Also, as you, I mean, and that's what I would do, with you can easily define something that roughly captures some of this. But the beauty of it is exactly that you have metrics that you can trust, that connect you know, you have the theorems underlying it that you can show some of the robustness, and you can show that it actually reduces down to the classic case and so on. So this is really cool, Renaud, and yeah, thanks for sharing. Did we get the paper, or is there more we want to talk about now?
I don't know if you want to. I can just tell you. So actually, here I gave like the theoretical motivation. So I can tell you that
Yeah.
if you're not too lazy, you can download the paper and you can jump to page 4 now. You're not obliged to write, or maybe to page 5. I don't know. The things that we used. So as any data science paper, what we did was I told you about this motivation from paper from math, right?
Yes.
What we somehow quantified was what would be the diversity of research papers, in the sense, do they tend to incorporate like concepts that are very different of each other, or do they tend only to have concepts that are very close to each other? And somehow we were able to do this kind of quantification, and something that we didn't do, but as a next step would be nice to see, well, if maybe certain research topics or certain authors tend to be the ones that possibly bridge very different ideas, right? Versus others who might be very specialized in a very like specific area of science. But that's something that's, well, we are looking for.
Terrible podcast hosting that I didn't follow up on it, because you gave the motivation from the product space and this idea. So this is a very cool kind of application of it also.
Yeah. And so I maybe if you don't mind, I'll just finish with one figure, and then I will.
Yeah, show it.
Just to discuss, right?
No, okay. But also, yeah, I want to see it. I'm excited. Yeah,
because it's a beautiful.
I read this paper,
and I know that Karel, who's been doing it, would be very happy if I show it. But
yeah,
because I want to get the Karate Club trophy. I don't know if it counts, but in any case,
we'll see if we can squeeze it in. The Karate Club.
No, but so basically, it's something that is quite interesting. So we started with this, right? And then a natural question that you may have would be the following. So if you have a graph, what is the distribution that maximizes the variance, right?
Yes.
And something that initially I had a very bad intuition. So I thought that, let's assume that I have a graph that is like this, right? Yeah. I thought, well, the one that is going to be maximizing my variance is going to be the uniform one. But of course, it wouldn't be the case. What would be the distribution that maximizes the variance? It would be the one where, for the same graph, you put all of your weight at the extremities. Yeah.
Yes.
Because that would be the situation where the things are the furthest away, and from the definition, you would have like an optimal variance. And so, from the nice mathematical property of this quantity, you can show all sorts of results, like in trees, the optimal, like the distribution that maximizes the variance is concentrated on the leaves, right? Yeah. But you can also show, like in some, like more numerically and giving some intuition, that in random geometric graphs, if you look where is located, what is the support of the distribution that maximizes the variance, actually it's going to be here on the boundaries of your system, right? So it means that all of the nodes where you would have a non-zero probability, yes, are the ones that are at the border of your system. Yeah.
Yes. It's not even a smeared outness. The intuition is more of a kind of really extreme. Yeah. So this also connects, I guess, to assortativity again, right?
Yeah, and it connects to this, and also to this kind of notion of what is the core versus the between the boundary of a graph, right? Yes. And because of that, something that we built was the following. So let's assume that you have a graph, right? And you look for the distribution that maximizes your variance. Mm-hmm. Well, in this case, that's in the case of the Karate Club, that would be all of these nodes that are in dark blue here, yes, that are basically the leaves. Here, and this one as well, it seems, and this one. What we do is, okay, so these are the ones that are the furthest away from the center. Yeah. And then what we do is we take them out from the graph. We have a smaller graph, and in this smaller graph, we calculate what would be the distribution that maximizes the variance. And that would give us this time these nodes that would be these ones in blue, I suppose, here, and this one here, these ones. And those ones are those that would be one step away from the border, right? And you continue to peel out somehow your graph always by removing those that are at the border as defined from this notion of maximum variance. And this is some sort of like an alternative way to look at this kind of K-core, or what would be core periphery type of organization that is defined somehow by all of these different, some sort of like layers that would be present in your system, from the nodes that are very, very far from each other to those that would be more in between, and so on and so forth. Yeah. And so it means that it was kind of funny, because it was clearly not the objective of the work. The objective of the work was essentially to solve a very practical problem, right? Yeah. We had this data. I had this data problem in mind for 6-7 years. And by deblocking the situation, looking at it from a different perspective, well, actually, we had all sort of like nice theoretical questions that came out along the way, but also some alternative way somehow to characterize networks. And here, in this case, to have some sort of like a core periphery decomposition that would be coming out of it.
Yeah, now this is beautiful. I mean, one of the questions, I mean, we have to stop, because we can't do many hours, but I mean, but I want to keep chatting. And I guess the intuition I want to pursue or look into is the connection to this and the entropy, because to get the Renaud entropy, you had to make this pretty local again, the distance. And here again, with the kind of the intuition you had was also that you would put equal weight on each node in your little example before, instead of at the ends. So this is not so entropy-like as was my intuition in the beginning. So it's also interesting to somehow compare this to a more entropy-like.
Yeah, I think that's,
if you go back, just very quick, but if you go back to kind of distributions of a single variable, it's the same thing, right? That the max variance, if these were two distributions, the max entropy would be the one that had the flat distribution, and the maximal variance, if these were, counts of values we had observed in just some variables, would also be. So I guess it also connects just to what the variance really means. So it still fits with variance, but this is, it's an interesting kind of question. Sorry.
No, and I see what you mean, and indeed, because so in a way, one way to think about it, there are a few mathematical tricks which mean that I'm hiding some stuff under the carpet, but I hope you don't mind. But the thing is that in a way, indeed, like if you have two completely independent variables, or three completely independent variables, right? What would be the optimal, well, the one that maximizes the entropy? Indeed, that would be something uniform, right? Now, in a way, what's happening here is that what we have is, it's as if we were to have like clusters, right? 3 clusters, and links that exist between them that become weaker and weaker and weaker. And in a way, when the 3 clusters are completely independent, well, basically each of these 3 sets of variables are independent, and we would be having this kind of like entropy-like interpretation, right?
Yes.
While if instead these links here become more and more important, then you start to have the distance between the parallel nodes starts to play a role, and now the optimal distribution will not be uniform anymore, but it would be something that basically goes into the extreme of the corresponding graph. Yeah. But I hid a few details under the carpet, and actually I'm not even fully sure that this is entirely correct. So that would be my kind of like
so cutting edge the science here on this podcast.
Okay, well,
we're not even sure it's correct.
So this is some sort of like an intuition. That would be the intuition that I have, and hopefully, well, it might not be correct actually. But, not such a long time ago with a student, we had an intuition, and we arrived at a result that was completely the opposite of the intuition that we had initially. And I know that he was a bit disappointed, and I was, well, no, that's just wonderful. And of course, I said it to cheer him up, right? But I also said it because I think it's true, right? Sometimes when you have something that changes your intuition, of course, it's a bit depressing, because it means that, well, I'm a bit lazy. You are lazy as well. You don't read papers. So we are lazy sometimes. We don't want to think too much. But on the other hand, it means that there is some deeper truth behind it. And it means that it challenges what we are thinking.
Absolutely. I mean, this is when we get smarter, is when we get something we're surprised by. I think that's where the gold lies, right? That's where the good stuff is hidden, is when we're somehow surprised by.
So I really hope that what I said is incorrect. Then I'm going to be having much more fun.
All right. I know this has been so much fun, and so good to see you. Thank you for taking the time. Thank you for going through the paper. I'm now, it's only a few podcasts, but every time people say, you really should read the paper. And so I promise I will, but really fascinating, great talk. I really enjoyed it. Any last words?
No, I just wanted to thank you. Thanks for the invitation. It was a wonderful experience. And looking forward to looking at the next episodes afterwards.
Yeah, all right. Thank you so much, man. And thanks for coming, and we'll talk soon. Take care.
Yep. Bye-bye.
Bye-bye.